talking about vectors and, well, linear algebra in the last lecture, but maybe before we get on to that, can I collect your homeworks?
I think that I sent you last week.
Sorry?
I think I have sent the homework to last week.
Oh, did you? Oh, yeah, that's
like
right. Yeah, that's right. Okay, thank you. All right. Okay. So I noticed there's some links here. How do I access the link?
I think I'll send you an email as well.
Okay. All right. Okay. Okay. Great. Yeah. So I was going to maybe briefly talk about the homework. Maybe look at some of these links, but because I don't have all of your links right now, maybe another time. Maybe what I will do is talk about the assignment a little bit, because I thought about that a tiny bit. So let me talk about that actually then. Oh. Okay, so as you know, the assignment is what, 20%, I think, of your final mark. So I thought I would introduce it kind of a bit early so that you sort of have the whole semester to think about it. And we've also got the Spring Festival break coming up. So I think that might be a good time for you to maybe get a head start on it. So basically the way that this will work is going to be pretty open-ended. You know, they're not going to be really, you know, like question type thing. So I'm just going to list 3 or 4 just ideas for assignments that you can basically choose. So you can just say, oh, I want to do number 1, number 2, that kind of thing. And we can basically discuss it further from there. So here are just sort of 4 ideas for assignments. So the first one is working with the IBM Queue experience. I don't know, have you guys heard of this? No? Okay. So you know, quantum computers were basically, until about 5 years ago, virtually non-existent, only in sort of universities, small-scale kind of places, you know, demonstrations. But actually, in the last 5 years, maybe say 10 years, things have really speeded up commercially. I think we talked about this already a little bit. And so some of the big players in the field, or big computing companies like Google, IBM, and Microsoft, they're all got quantum computing efforts now. And the way that they've decided to sort of go forward with this is that you know, they have these hardware quantum computers at, you know, various places, and you know, they're not very big. So these quantum computers might only have, say, 20 qubits, something like this. So of course, you know, much smaller than a regular computer. You know, got, you know, billions, trillions, or something kind of storage. So you know, these are relatively small scale. But what they're doing is that they're offering access to the quantum computers that they have on the cloud, just for anybody to use. So, of course, you know, kind of a free, I think you can get like free accounts that you can do this. You get like a small amount of time on the quantum computer. You know, you just register with your email, and you can run a few types of circuits. Well, no, I mean, you can run any circuit that you like within the limited kind of constraints of what they can do. So the first topic is basically, well, make an account on IBM Queue. Okay, so that's not so hard. Maybe the hard part will be to learn how to actually use it. I just had another quick look today. They've made it pretty kind of, relatively easy to use. Some of my graduate students have tried to use it, and people have even written, research papers using it, that kind of thing. So the task is to program and run a quantum circuit on it. So they already have some demo examples. So of course, if you just run the demo, it's not much fun. So I suggest that you run a circuit which is not there already. In fact, you should run something that's not there. So I looked at the list of algorithms that they have sort of pre-programmed, and I think quantum teleportation is not there. Quantum teleportation is you can do even with like 3 qubits, so you don't need many qubits, and you can actually do something, well, pretty cool, quantum teleportation. So that's an example of a quantum circuit. So, say if, I don't know, 2 of you, 3, all of you want to do this project, then I'd be happy for you guys to both do the project, but maybe you would do slightly different circuits or something like that. Right? So maybe one of you do quantum teleportation, and another one you do something else, just so that you don't overlap. I think having a project that is separate for each person is kind of what I'd like to see. So you'd run it, and then you'd analyze the data from the machine, and then show that it's been correctly performed. So, I think this would be quite an exciting kind of project, because you're actually really using a quantum computer. It's, 5 years ago this didn't exist, and now you can do this. So this is really, really new stuff. So it's kind of an opportunity to do something like that. So that's for somebody. The first topic might be for somebody who's kind of, really wants to get their hands dirty with quantum computing. The second one is more sort of a conceptual one. So if you are the type of person that's more interested in sort of, fundamentals of quantum mechanics, strange philosophical questions, kind of puzzles of why quantum mechanics is so weird, this one might be more for you. So there's a famous kind of thought experiment called Wheeler's delayed choice experiment. Roughly speaking, this is sort of an experiment where it seems like quantum mechanics seems to make, no, I'll leave it to you to figure out what it was. I'm going to try and explain it, but it's too confusing to probably explain it. But anyway, it's sort of like a thought experiment where it really shows the puzzling nature of kind of quantum mechanics, and it's one of these sort of classic types of weird, paradoxical thought experiments, a bit like Schrödinger's cat, but kind of a bit different. So the aim here would be to sort of understand what this experiment is, explain what the paradox is, and of course, you have to present it in front of everybody, so you'd want to, be able to explain it to everybody else as well, not just me. Show using some mathematics how this works, and maybe discuss some of the more recent developments, because people have done real-life experiments using this. Another one is like if you're more the type of person that wants to do coding. So if you're quite proficient at coding, I'm sure you all can code to some extent, but maybe some of you really like that kind of thing. So you would write some code in the language of your choice. So Python. I use Mathematica a lot, MATLAB, whatever you like, and simulate quantum algorithm. So this will really get you kind of practice with how a quantum computer works. I think when I was like a graduate student, I was just starting. I think you learn about all these things in books, but you feel like you don't really understand it unless you do something with it. And coding is a really very tangible way of sort of kind of understanding how stuff works. So even if you derive it on paper, sometimes I feel like I still don't really understand it. But if you code it, it's there in numbers. You have to understand what's going on. So I think it's a really good way of understanding what's going on, just to code something up. And so you should write the code so that it's relatively easy to, reconfigure your code to, so it's not just like running just the one algorithm, but, if I said, okay, can we just change this gate to, put it somewhere else, then it should be relatively easy to do that. So, more or less up to you how you write it, but something so that it's, not just a single purpose kind of thing. Demonstrate that it works by running a well-known algorithm. Topic 4 is very much like topic 2. So this is again one of these sort of weird paradoxical effects, interaction pre-measurements. So there's this thing called the Weidman bomb, which is apparently some way of knowing whether like a bomb is somewhere without even interacting anything with it. So if there's like a bomb, and you shine light on it, it would explode. But there's some funny little trick that you can do to show that you can figure out whether the bomb is there or not, even without any light going through it. So some kind of weird kind of quantum effect again. So they're very much like topic 2. So this is a little bit more conceptual. So those are just 4 ideas, but I'm happy for you to do any kind of topic. If you have some burning desire to do something specific, then come and talk to me, and we can discuss it, and I should be able to sort of point you in the right direction. So yeah, by the way, with these things, I think it's very helpful that you sort of come and discuss with me every now and then. So they are kind of open-ended. So you can kind of do whatever you like with them to a certain extent, but with great freedom also comes great responsibility. So you should, not just turn up on the last day and said, okay, here's my piece of work, and it might not really be the thing that I'm kind of looking for. So it'll be helpful if you sort of come and discuss with me every now and then. So, but of course I'll come and check. Okay, so any questions? I uploaded this to NYU classes.
So do we need to present it at the end of the class?
Yes, so towards the end of the semester, but not really right at the end, we can decide exactly when. I'll ask you to come up and give just a short presentation of what you found. You can even do it earlier as a sort of a work in progress, so you can just about choose when you want to do it. One way to do it is to do it, sort of halfway through, show me what you've got, and we can discuss it. That would be the kind of feedback that you could incorporate towards the end. But probably most people will want to do it towards the end of the semester. Okay. Alrighty. So let's get back to what we're talking about. So I think we got up to, conjugate vectors. Yeah, so we have these sort of dual quantities, which are conjugate vectors, and these are also vectors, but it's best maybe to picture them sort of as row vectors. and they have complex conjugate components. So the real kind of place where they come into where we'll be using it is particularly in this quantity, which is the inner product. So this is where you take a conjugate vector and a regular vector and you turn it into a single number. So the way it works is a lot like the dot product, except that the conjugate vector has the complex conjugate components. So when you add them together, you have to make sure that these are complex conjugates rather than regular components. So the way to understand how, or to say or to interpret what this actually means is that one important kind of measure is to if you take the inner product of two vectors, so say you've got the vector alpha, the vector beta, so you first find the conjugate version of your alpha, take the inner product. So if these are 0, this means that basically that they are orthogonal. Right? So you can imagine this as being in some space. So here's beta and here's alpha. Now if they are sort of 90 degrees in this space, then this will always give 0. So of course, a simple example. So a simple example of this would be so these two unit vectors here. If you have the unit vector say 2 with unit vector 1, these are of course right angles to the to each other. So this would be 0. Let's adjust something. And in row and column vector language, so E2 is, in terms of column vectors, this would be like 0, 1, and this is row vector 0, 1, 0. And of course, if you do that multiplication, then this will be 0 because these are orthogonal. But so that's a simple example, but you can have more general vectors. So if you have, say, some vector psi, and then say the components are like this, cosine and sine, and then if you have another vector, and the components are say minus sine and cosine, then these guys will also be orthogonal. Okay, so more properly I should write transpose here. So this one is a regular vector, so it should be this way, but I've written it this way. Transpose or row vector is a column vector. Okay, then if I calculate phi and psi like this, then I'll have cosine sine minus plus sine cosine, and this will equal to 0. So it doesn't have to be along these axes. It can be sort of any angle. So if it's right angles, then these are orthogonal to each other. And of course, so we could kind of plot this like this. So the vector cosine sine is, of course, some vector like this. Right, so the x direction is cosine, y direction is sine. This guy is going to be basically that vector, but so the x component is minus, and the y component is plus. So this is going to be basically some vector which is pointing in this direction where this is 90 degrees. So this would be, this guy would be phi and this guy would be, sorry, this is psi and this one is phi. Okay. And actually this quantity is used a lot in quantum information. It's called the fidelity because it basically, because actually what we'll see is that the quantum state is represented by always a vector like this. And so a thing called the fidelity is often used because often, we're running a quantum computer and then the final output should be something, but because of noise and all these things, you get something slightly different. So this is kind of a measure of how good your calculation was, because say alpha is what it should have been and beta is what you actually got. And so you talk about stuff like, 99% fidelity basically means that the state that you actually got was within like 99% of the state that it should have been. So these things are often used. Okay. So other quantities that are related to the inner product are things like the norm of a vector. So the norm of a vector is like essentially the length of the vector. So in these examples here, say the norm of psi. So what's the norm of psi going to be here?
Square root of 2?
No. So psi, we're doing this one overlap with this one. So it's cosine, sine, and then the column vector version. So,
1.
yeah, 1. So cosine squared, sine squared, of course 1. Yeah. So the length of that vector psi is equal to 1. And of course these vectors like E, these are unit vectors. Of course they have length of 1. That's why they can be called unit vectors. So in quantum mechanics, actually, generally all our vectors are always norm 1. And this is basically because eventually we interpret, or there's a relationship between the vector length and the probabilities. So for example, for this one, probability of it being in this vector is like this coefficient squared. And the coefficient, the probability of it being in this one is this one, mod squared, norm squared. And of course it has to be in either one, so these things have to be sort of, the total probability has to be 1. So that's why we normally deal with vectors that are unit norm. But of course, at the level of, I haven't really started talking about quantum mechanics here. We could equally, of course, have vectors that do not have unit norm. So, for example, here, if we have a vector that, say, is not of length 1, we can easily convert it to one where the length is equal to 1 just by dividing the length of the vector by its length. Sorry, dividing the vector by its length. Right? So this is the original vector, which might have a length bigger than 1, right? Then you find the length of the vector, which is square root of A overlap with A, inner product with A itself, and then just divide that vector by this number, and then of course you have something with then unit length. So we can of course show that it's definitely unit length because, so in this example, if we have alpha inner product alpha, then conjugate vector of alpha dash is alpha. Remember, this thing is just the number, and I'm just taking square root of that number, and this is the conjugate vector. Okay, so I just do my kind of matrix multiplication there, and so the top part is just, well, these are just numbers, so we can just kind of factorize this factor out here. There's a square root here, so it's just that, and then that multiplied by the inner product of alpha and alpha, and then of course these are the same, so that's equal to 1. Yeah. Okay. Right, so let's do a quick spot quiz. So, you might like to use something to write with. So let's find the inner product of alpha and beta. I'll do it in my head.
The 2 minus 3i.
2 minus 3i. Maybe I did something wrong. Yes, 2 minus 3. Yes, 2 minus 3i, exactly, yes. And so next one is normalize alpha. So you'll have to find what the normalization factor is. Do you have it?
Is that so we basically divide every scalar with the square root of 5.
Ah, 5. Yes, except I think it's not the square root of 5. Oh, no. Oh, yeah, okay, you're right. Square root of 5, yes. I can't do mental arithmetic today, yes. So 2 squared plus I mod is 5, and square root of that is square root of 5, exactly, yes. Okay, so the normalized version will be 2 over square root of 5 of E1 plus I over square root of 5. So, sorry, that's not alpha, that's the normalized version, so I should call it something else, maybe alpha dash or something. It's a normalized version of alpha. Okay, that's good. I think you're doing better than me in my mental arithmetic today. Okay, so operators. So we've dealt with vectors, and that's fine too. In quantum mechanics, what we'll find is that basically describes the state, but in a quantum computer or even in some physical process, actually this state will change. So just like you throw a ball, the position and the momentum of this ball is changing all the time. So you could say that that's like a state, classical state of the ball. It's the x-axis and the y-axis and the momentum are changing all the time. So in the same way, in quantum mechanics, because vectors are now going to describe the state of our system, this will also change with time. And the way that we describe changes or processes that change the state of the vector. So, if I have a quantum state here and I just flick it or something, of course, it will change. So the operation of me changing that state is done by something called, mathematically done by something called an operator. So we have operator is basically always something that takes some state and then turns it into a new state. So it's like some kind of machine, if you like. So it's like, imagine some machine, I put in some vector, and it does something to it, and out comes a new vector, and it's the result of this operation on the vector. So in quantum mechanics, actually, all operations are always linear kind of vectors. So what linear means is that if I had some superposition, so basically sum of these two vectors, then a linear operation means that the final result is actually just the same as operating on each of these two states individually and adding them later. So, even if we had some combination of two states, we can always work it out by finding what the result is on each individual component. So, so in a way that makes our life kind of a lot easier in quantum mechanics. Okay, so such things are actually perfectly represented always by matrices, because matrices have exactly this kind of linear property. So, so actually any operation in quantum mechanics is always going to be represented by, well, we could write it as some operator like this, but we can always also write it in terms of some matrix. So, in component language, so this is how you would write it in this kind of vector language, but we can equally write the same thing in terms of matrix multiplication. So, if this A, which is like components of the original vector, so A1, A2 to AN, that's our original components, and some operation which acts on this state is going to be just a matrix multiplication acting on this original components, and then that of course makes a new vector, right? Because you do matrix multiplication, or from this row vector multiplied by this matrix, do matrix multiplication, one goes on the top there, you add up all those things, and then you get a new vector. So, so that will be kind of the component way of writing it. So remember, these are all components like this. And each one of the new components, so I didn't quite write that here, but the alpha, try to mimic A2 dash to AN dash. And matrix multiplication, where this Tij, which are all these little elements of the matrix, is always written in this form where you have sum over the second index, and then this makes a new vector. Well, these are all the components of a new vector. Yeah, so there's a few kind of different ways of writing the same kind of thing, right? So this is sort of the vectors in some space. So you just think of them as sort of entities, vector entities. This is just a list of kind of component numbers, and these are the individual numbers that are inside these components, right? Okay, so the elements of the matrices you can always write. So here, this is a little bit more like this notation here. Well, it is this notation. So this T is the matrix sort of itself, and we can always represent that matrix in particular kind of basis choice that we're doing, a bit like how we represented our vector. So here's our vectors in terms of the E1, E2 unit vectors. So in the same way, we can write all the matrix elements of this operator T by kind of sandwiching it between these unit vectors. Because essentially, for example, this component, let's say T21, what that means is that this operator T, it acts on, say, unit vector 2, so E2, and then it produces unit vector E1, right? So that, and basically this number is like the coefficient of that. So we can relate these two ways of writing it. So this is sort of the matrix itself, and this would be the way that you relate the coefficients here. And notice that this thing has this sort of outer product thing, and this thing is basically for each matrix element here. This is the object that turns a state from Ej, like unit vector Ej, into state Ei. Okay, so maybe that might not be perfectly clear. So let me just then explain what this outer product is. Okay, so we'll maybe try and revisit that this notation of the operators here. So we saw the inner product. The inner product was something where we have basically these two vectors. This takes, here's the vectors, and here is the conjugate vectors. These are two sort of dual spaces, and then they come together, and you can do an inner product, and then that forms a number. The outer product is actually a way of more writing this a matrix like this, and so maybe a simple example could be written like this. And so the key point here is that the ordering of these things is of course different, right? So in inner product you have a bra and then a ket, but here you've got a ket and a bra. And the reason why it's this way around, so let's first look at it in terms of this the component notation, right? So here's a vector, that's a column vector. Here's a conjugate vector, that's a row vector. Now, if we have it in this order, we can still do the matrix multiplication, except that actually, remember, we have to take this row and then multiply by this column, right? So actually this product produces a matrix like this. So if you go through and work out all the different 9 combinations, the only one that is not 0, because all these are 0, is actually this corner, because this is like the 3rd column and the 1st row. So 3rd column, 1st row is equal to 1. So this is what you call the outer product, and essentially this produces kind of an operation. And let's just do a couple more simple examples with that. Okay, so of course, so this E1, E3. So this, as I write in the slide there, is equal to this matrix. And the main feature of this particular matrix here is that if you take, so let's try multiplying this with the 3 unit vectors. Okay, so when I do the matrix multiplication of this and this one, what do I get?
0.
Yeah, so it's all 0. So 0. What about this one?
0.
Yeah. And this one?
The same.
Same, meaning
0, 0, 1 is a
0, 0, 1. 0, 0, 1 or
1, 0, 0.
Yeah.
Actually, it's the
One.
3rd column.
1, 0, 0. Exactly, it's the 3rd column. Yes. So this thing has, well, the property, if you like, of being only equal to well, something non-zero firstly for the 3rd column. So essentially, you're right. So these are basically just picking out the 1st column, 2nd column, 3rd column of this matrix, and a way to actually do this or see this in a slightly different way using this notation goes something like this. So this one, so you would say, okay, so here's my matrix E1, E3. I'm going to say multiply it by E1 vector. Okay. Now I know from what the stuff I'm doing here, E1 and E2 are orthogonal. So because I know E1 and E3 are, well, in this case E3 are orthogonal, I know that when these guys, so this one, it becomes like the inner product. So this is E3, E1. And I know immediately that's 0 because E1 and E3 are orthogonal. So we can repeat the calculation here. E3, E2. I know this thing is 0, so this is 0. It's actually 0 vector, but okay. And here E1, E3. So here it's actually the same vector. And E3 with itself, E3, this is basically like doing something like this, 0, 0, 1, 1, 0, 0, that's the length of itself, and, and it's length of itself, and so it's 1 squared, which is 1. So this is just 1, and this gives E1. Okay. So after a while you sort of immediately just sort of recognize this thing as a sort of something that has this pattern. But essentially the way that you view this is that you've got this side in order to say that, okay, it's only E3 that's going to give me like a non-zero value, right? Because the only thing that can hit it when you have, you know, this thing here, E1, E3, and then, you know, I've got some state that this is going to operate on. The only thing that's going to be non-zero is going to be E3, because that's the property of these inner products, right? And then so these two things combine into some number, so it's either going to be 1 or 0, say, and then the final result is, here we've got our vector here, so it's going to be some number proportional to basically E1, and then this proportionality could be either 1 or 0, depending on what this inner product turns out to be. Okay, so again, this is not really a mathematical explanation. This is just sort of trying to kind of convey to you how this sort of notation kind of works, and the reason why we can kind of write, well, firstly these types of matrices, or like firstly why this is a matrix to start with. Basically because it's, you know, when you come in with this quantity with a vector, this part of it actually just turns into a number, and then finally this turns into a vector, right? Because this, when you have an inner product, this part of it is always just a number. So this is why this is the form of a matrix. It's basically because it's like, here's the part that's going to collapse to a number, and here's the part that's going to be a vector. Okay, so that's why this is, say, turned into this matrix. Now, we can actually form, you know, we can put this 1 in any place that we want. So if we want to find the 1, say, right in the middle here, it would be like 0, 1, 0, 0, 1, 0. That would be picking out that one. This one here would, of course, be something like 0, 1, 0, and then 1, 0, 0. So we can pick out any point in this matrix. And then if we put a coefficient on it, remember these are just numbers, and then just go through each of these matrix elements, put the right number in it, then that constructs any matrix that we want. So that's basically why this thing corresponds to sort of this operator. That sort of makes sense. Okay, all right. So that's our operator T. And if we want to say just do a straight outer product, so here I only did the outer product between just two simple vectors like unit vectors here, but there's nothing that stops me from doing the outer product between slightly more complicated vectors. Again, the rule is the same. Here I'm basically just doing a matrix multiplication, but because of this ordering, column vector then row vector, I end up with a matrix, and of course it's like, you know, this element, that one becomes the first element, so forth. So I get like an n by n matrix. Okay. Right, so let's just do this one quickly then. So, did do that right? Yeah, so Z is a matrix here. So happens to be that thing. And alpha is this vector. So the first thing is just to multiply those two together and find the new vector.
I think the first one is just add a minus sign on the one at the bottom.
Yep, that's right. Yep, correct. So basically just do a matrix multiplication of this one and this one. So the first one will be, first element will just be the same as this one, and the second element will have a minus sign for multiplying those two. Okay, and then number 2 is use the above result to find this, which is beta conjugate vector times whatever you just found. So you can, because you've already worked out what this part is, so basically just pick the inner product of beta with whatever you found in the first question.
Is that
0.
No.
1.
1, yes. So it is 1 because if we agree that the first part was square root of 2, so beta, so remember we've got to, when we do this one, we've got to take the complex conjugate and then make it a row vector, but they're all real numbers, so you don't have to do anything. So we agreed that this one was 1 minus 1. Sorry, I think I'm missing something there. Yep. Okay, so these scalars just come out, it's a half. And then we've got just 1 minus 1, 1 minus 1. Then it's a half of 1 plus 1. So 1 plus 1 is 2, and 5 by 2 is 1. Okay. Oh, that's the end of that one. Okay, well, we might make a start on the next one, which is still linear algebra. So before I forget, why don't we make, because next week we've only got one lecture, right?
Yeah.
Thursday is the beginning of spring holidays. So because ordinarily homework will be due on Thursday next week, but there is no Thursday next week. So can we make the homeworks due on Tuesday? But the next homework is actually quite easy, I think, at least for you guys. It's just about complex numbers. You'll probably breeze through it anyway. So let's make the homework due next week, Tuesday. And then over the break, maybe I'll give you the linear algebra.
So we'll do homework 2, 3, and
No. Just homework 2 is
Okay.
due next Tuesday.
okay.
Yeah, that's all. Because there is no Thursday next week. Okay, so we'll just make a small start. We've only got a few minutes left. So, right. So this set is a little bit more about how matrix manipulations work. So as Danny pointed out, this kind of operation of transposing, which is of course basically when you interchange the rows and columns of a matrix. So if you have the original matrix, it looks like this. T1, 2, so forth here. Transposing it, basically you go on the diagonal here, and if you swap all the elements, then you get the transpose of the matrix. So whatever this element here is, it gets swapped over to that. So some special types of matrices have particular sort of symmetries. So if the transpose matrix is the same as the original matrix, then it's called a symmetric matrix. Sometimes you get anti-symmetric matrices where it's the same matrix except that all the other have got an overall minus sign. Another different operation, of course, is the conjugate of the matrix. So if you take the conjugate star of the matrix, then that just means all these elements, you take the complex conjugate of it. And of course, you can have real matrices. So just like with regular numbers, if you take the complex conjugate, it's the same matrix, then it means it's basically all the elements are real. So you need basically all the elements to be real for the matrix to be real. Purely imaginary matrix, as you can imagine, all the elements are purely imaginary, and so if you do that, then taking the conjugate will bring out a minus sign because the complex conjugate of I is minus I. And the thing which will be most important in quantum mechanics is actually the combination of these two. So usually it's called the dagger. It's called the complex conjugate. The symbol is dagger. And so it's taking the complex conjugate and taking the transpose. And well, basically the reason why this is important in quantum mechanics is because well, I guess there's a mathematical theorem that says that if you have a matrix like this, always basically the eigenvalues, which we'll talk about in a few slides later, are always real. So even if you've got complex numbers here, you have eigenvalues which are real, and eigenvalues turn out to be kind of quite important in quantum mechanics because they basically link to sort of observables, physical observables, and physical observables always have to be real. So there's some, you have to get real numbers out of quantum mechanics, and this is kind of a restriction that you need to have mathematically in order to have kind of real observables. Okay, so I think we'll just leave it there and continue next week. Any questions? Okay, great.